All right, two theorems on the board. Mean value theorem and Rolle's theorem. Mean value theorem and Rolle's theorem. So what these are doing is talking about in general about a graph. They're actually pretty simple theorems. There's not a lot to them. They sound very complex. Okay, so we'll work with the mean value first, and then we'll go over to the Rolle's theorem. For the mean value theorem to work, all right, think about the word mean. Mean means average. Finding a mean of a set of numbers, that's an average. It's talking about some sort of average that's going on. The key words in this would be continuous, differentiable, and the fact that the endpoints are not the same y value. Endpoints are not the same y value. So let's say we have an interval of, say, 0 to 7. Well, if you substitute a 0 into the function and a 7 into the function, you get two different y values. They're not going to be the same. That's all it's referring to. Right? Is the function continuous? Most functions you know by just looking at them if they're continuous. Okay? You don't even need to see a picture. You know what a continuous picture looks like. But let's say I gave you some functions here. Something like, hey, you know what? Is this graph continuous? Absolutely. Okay? Even if it's one, let's say a larger polynomial that maybe you don't remember the picture so well, 3x to the fifth plus 4x cubed minus 2x squared plus x minus 7, you still know it's continuous. There's nothing in there that's going to create a domain restriction. Everybody okay with that? Now, you do have functions that have obvious domain restrictions. Let's do something like 3x over x minus 2. Where is that not continuous? At 2. There's a problem there. It's very basic to us. Right? If I asked you to investigate this function on the interval from 3 to 9, that's a continuous function. Because I'm only asking you to look at the interval from 3 to 9. And the problem was at 2. Does that make sense to everyone? If I said the whole thing, then it's not continuous. If I said, hey, let's look at it on 1 to 9, okay, wait, it's not continuous. All right. So when we're saying continuous, we're talking about that interval. Not necessarily the whole graph, but on the interval we're supposed to be looking at it.
How's 3 to 9 continuous with 1 to 9 is 17?
Because where is it discontinuous?
Oh, 2.
And 2 is sitting right between 1 and 9.
Okay.
All right. So we just talked about, on the last one of the homework questions, oh, this guy. Is that graph continuous?
Yes.
Yes. However, that graph is not differentiable. Comes to a point. It's that V shape, right? So if our functions must be continuous and differentiable. So all those ones I had up there before, they're continuous. They were also differentiable, means you can find a derivative at any value within the interval we're talking about. This one's continuous, but it's not differentiable everywhere. Where can you not find the derivative of this? What x value? 5. That's where that point would be, right? Because this graph was shifted to the right 5. And so it's creating that point. All right. There it is right there. Because we're having a problem. So 3 things we need to happen for the mean value theorem to occur. All right. Now let's go through some things we've talked about. All right. The derivative, slope of the tangent line. How many tangent lines does a function have? An infinite number of tangent lines. You can draw them at every point along there. Everybody okay with that? All right. So this left side of the function, the derivative, is referring to that slope of a tangent line. You see that f prime. This piece over here, that should look really familiar. You first saw it like this. It's just your old slope formula, right? Y minus y over x minus x. So we just have function notation, still y minus y over x minus x. Just an old slope formula. All right, so let me give you a picture for this. If we have some function here, We'll call this A, f of A. We'll call this B, f of B. So just 2 points on the graph. The solid line's our function there. Okay, so let's think here for a second. All right, if I'm looking at that solid line, f of A and f of B, they are different values. I don't know what they are because I don't have numbers up there, but I know they're different. Everybody agree?
Yeah.
No problem there. Okay. Is this nice solid line continuous? Yeah. Is it differentiable everywhere?
Yeah.
Yeah. Okay. Matter of fact, let's think about it here. We'll review what we've talked about. Differential refers to slope of the tangent line. It's positive, positive, positive. It's getting less and less positive, approaching 0, maybe about right here. And then it starts turning negative. Everybody agree with that?
Yeah.
Okay, so we have, unlike y values, it's continuous, it's differentiable. We're good to go there. That means there must be a point C. So there's got to be a point along this curve somewhere where this definition is satisfied, where f prime of C is equal to f of B minus f of A over B minus A. Those pieces. Now, the things on the bottom. This is the secant line going through. Does that secant line have a slope that's positive, negative, or 0?
Positive.
Positive. Now we don't know how positive because I don't have numbers, but I can tell it's positive. Does everybody agree with that?
Yes.
Okay. What this is saying is there is a tangent line up in here along the curve that has the same slope as that secant line. Now, if 2 lines have the same slope, from your old basic stuff in middle school, that means they're parallel. Do you agree with that?
Yes.
Same slope, parallel. So just kind of visualize, I'll draw it up there, but just kind of picture roughly where the tangent line would be on that curve that would be parallel to the secant line. Something that's going to be parallel to it. And we should see somewhere about right up in here. Everybody okay with that? So if I drew a tangent line up in here, pretend my drawing looks really good. There's my tangent line, and there's some value C. I guess that would be the point C, f of C. But there's some C value in there where the slope of that tangent is equal to the slope of the secant. Everybody okay with that?
Yes.
Average rate of change versus instantaneous rate of change. This shouldn't be new terminology. Maybe this is. It's instant kind of stuff. Okay. We've actually worked with it some. Average rate of change. Okay. All right, we have said that the slopes of the tangent lines, positives, 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 somewhere up in here is 0 and then turns a little bit negative. Everybody agree with that?
Yes.
So wouldn't you say there's way more positives than there are negatives?
Yeah.
Everybody agree?
Yes.
So if you're going to average a bunch of things with positives and negatives, and there's way more positives, wouldn't the average be positive?
Yep.
Makes sense, right? This is the average. Secant slope. This is the average rate of change. So if I found the slope of the secant line, the average rate of change is f of B minus f of A over B minus A. Now, what you most commonly found the slope of was you looked at a linear graph, you found 2 points on a linear graph, and you calculated the slope. You said, well, hey, that's the slope of the line. That's also the average slope of the line because it's the only slope of the line. If a line has a slope of, say, a 3, it's a 3 everywhere. So if you add 100 values of 3 and divide it by 100, you're still getting 3. Everybody agree with that? It never changes. Now you're looking at curves where, hey, it does change. So the slope between the endpoints would be the secant line, and that would be the average rate of change, that slope of the secant line. Everybody okay there?
Yes.
Slope of the tangent line, what do we know that as? Derivative. All right, so the slope of this tangent line, all right, would be f prime of c. So f prime of c is slope of tangent, which is also what we call the instantaneous rate of change. It is the rate of change at that very moment c. Not before or after c, but at that moment. Easy example. Driving the car 60 miles per hour. You throw something out your window. It's going 60 miles an hour at that moment. It might slow down really fast because there's no force behind it pushing it. But when it leaves that car, it's going the same speed as the car. That makes sense? There's a different kinds of force there. It's leaving at that same speed. That's why I can remember back in the day when, because you didn't get as much trouble back then as you do now. If you threw like an orange at a stop sign or something going down the road, it could knock the whole sign down. Because you're throwing it while you're going 70 miles an hour.
So if you're going at like 80 miles per hour if you're a hard pitcher.
Yeah, and that thing is just going. It's not like you standing there and going, hey, how come the sign didn't fall? No, there's some force behind it, a lot of speed. Okay? Get down the road and do that.
I think we have to try this sometime, see if it's true.
Yeah, we gotta test
If you got in enough trouble like I did as a kid, you knock mailboxes down. Well, yeah, if you're in the back of the truck and doing it, you're going 25 miles an hour, that's an extra 25 miles an hour of force hitting that thing. Different than just standing there. Okay? So there's that instantaneous piece that we're talking about. So at that moment, okay, at that very moment, this has the same rate of change as this guy. That's all it's referring to. It's equaling the average. Does that make sense to everyone? It's a pretty basic concept. It just really gets kind of confusing when you start reading through it. Now, you can have more than one point C in there. Let me give you a graph, something like this. Okay, so if I had this was the endpoint. All right, that would be the secant line connecting the endpoints. Okay? Is the slope of that secant positive or negative?
Negative.
Negative. Okay? And that would be the average rate of change between those 2 points. All right, and the reason we say the average, just kind of look at what's going on here. You got a couple zeros. We got some positive slopes. We got some positive slopes here. We've got a whole bunch of negative slopes. All right, so these negatives are basically outweighing these two positives. That's why the average is negative. That makes sense? Okay. Now, that means there's actually a couple places where you have a tangent line with the same slope. Again, pretend my graph looks good. Those should look parallel. I actually have 2 points on that graph where this could happen. So it's not always just 1 point. You could have more than 1 point where the instantaneous rate of change is the same as the average rate of change, or the slope of the tangent is equal to the slope of the secant. Everyone okay with that? The key is, look at either one of these graphs. They are continuous. They are differentiable. The y values at the endpoints are different. If those 3 things are there, the mean value theorem does apply, and we just call it MVT short. Something like that. Are you okay there?
Yeah.
Okay, now let's get a couple equations up here for mean value theorem, and then we'll talk about rolls. So let me get one up here. Let's say apply MVT. All right, so let's go with f of x equals 2x squared plus 1 on, get that n on there, 0 to 2. Now 2x squared plus 1, that's continuous. No problem with that. That's differentiable. Let's check the endpoints. Okay. F of 0 would be 1. F of 2 would be 9. Everybody agree with that?
Yes.
So continuous, differentiable, endpoints are different y values. I'm good to go. Okay. So I'm going to check f prime of x. So I'm going to look at slope of tan, and this is good to have in your notes. I want to find out where that's equal to the slope of secant. And I'm talking about secant line and tangent line. I'm just abbreviating. So slope of tangent, that would be 4x. That's the derivative. Slope of secant, 9. I'm looking for where this happens. 9 minus 1 over 2 minus 0. F of b minus f of a over b minus a. So I'm looking for where 4x equals, what's that, 4, right? This happens at x equals 1. And that interval, and that just so happens to be right in the middle. Don't look anything into that. It's not always in the middle. Okay? But at x equals 1, the slope of the tangent would equal the slope of the secant. So we want to remember this part here, derivative is my slope of tangent. There's my old slope formula between the endpoints. That would be that slope of the secant. Everybody okay there? All right. Look at a different one. Let's say f of x equals x cubed plus x on 1 to 2. On 1 to 2. I'm going to check my endpoints first. I need to make sure they're different. So I'm going to find f of 1 and f of 2. F of 1, 2. F of 2, what would that be, 10? So we're good to go. We got continuous, we got differentiable, y values are different. Okay, so let's take a look. I'm looking for where the slope of tangent equals slope of secant. I'm looking for where this is going to happen. Slope of tangent, 3x squared plus 1. Take my derivative of my function, that represents the slope of any tangent line. Slope of the secant, connecting the endpoints, 10 minus 2 over 2 minus 1, which means now I have 3x squared plus 1 is 8, and that's what I'm solving for. Everybody okay with that? And so I'm going to subtract the 1, divide by 3, I get 7/3. Everybody agree with that? We're going to square root, yeah. So x squared would be 7/3. All right, so that means that x equals square root of 7/3 or negative square root of 7/3. And I'm going to toss out the negative one. Why?
Because time value can't be negative.
That's not in the interval. That's between 1 and 2. And the square root of 7/3, get your calculator out and get a decimal. It is between 1 and 2, I'll tell you that. 7/3 divided is about, what, 2 1/3, 2.3. You take the square root of that, you're going to be between 1 and 2. So I would have that piece. So sometimes when you're solving, you could get a value that doesn't apply. It's still got to be in that interval. Everybody okay with that?
Yeah.
All right. Rolle's theorem. Rolle's theorem is a little quicker because it just kind of is a special case of the mean value theorem. So piggybacks on what was already said about the mean value theorem. Continuous, differentiable, keywords here. Function's got to be continuous, got to be differentiable. We talked about that. And this time, f of a has to equal f of b. So in other words, the endpoints would be the same value. Now, if that happens, then f prime of c is 0. This really is still the mean value theorem. Okay. Rolle kind of cheated a little bit here. When the mean value theorem was brought up, it was stated specifically, hey, when f of a doesn't equal f of b. So basically, it was implied that they could be equal, but it wasn't stated. It stated that they're not equal. Mr. Rolle comes around and goes, well, what if they're equal? I can get my own theorem.
Yeah.
Well, here is your mean value theorem. I'm just rewriting what was over here. Now, wouldn't if f of b and f of a be the same value, that'd be 0? Yep. So if f of a equaled f of b, then that equals 0. So there's Rolle's theorem. Hey, this guy equals 0.
Wow.
But that happened a lot in math. Somebody finds one little change and kind of makes it, hey, you know what? If I found that, I get my name in the books too. For all time. So it's really the same thing. So here's graphically what it looks like. Graphically, we're something like this, where this is horizontal. Secant is horizontal. What's the slope of a horizontal line?
0.
So what tangent line has slope of 0 at the max or min? Still parallel. Slope of the tangent still equals, I'll just say tangent's horizontal too. Slope of the tangent still equals the slope of the secant. It's just that 0 pops in because the two end values are the same. It's going to create a 0. So pretty much the same idea. And you've seen graphs where you could have more than one min or max where the slope of the tangent line is 0. Okay? So all it's saying is, hey, you know what? If I have a function where somehow or another my endpoints are at the same y value, then there's got to be a c value, sometimes more than one, where the slope of the tangent line is 0. So if I leave this point and I want to get to this point, and it's going to be a continuous differentiable function, it has to create a place where the slope's 0. Because it's still continuous and differentiable. You okay there? So really the only difference between the two, mean value theorem is under the assumption that the two end values are not the same y value. Rolle's theorem is under the assumption that they are the same. And that's what's creating the 0 on the end of the formula over there. It is really still this same formula, this fraction just reduced to 0. That piece. Everybody okay with that?
Yeah.
Okay. So if I looked at Rolle's theorem, let's get one up here for Rolle's. Let's go f of x equals sine x on 0 to 2 pi. So what we're going to do this time is Rolle's. So that means I'm still checking the endpoints. The mean value theorem, I want the endpoints to be different. For Rolle's to apply, they've got to be the same. F of 0 is 0. F of 2 pi is 0. Sine is 0, 0. Sine of 2 pi is 0. Everybody okay with that? Yeah. Hey, they're the same. Sine function, that's continuous. It's differentiable. You know what that kind of looks like. Rolle's theorem can apply. So we're going to look for where the slope of tan equals 0. The derivative of cosine, or derivative of sine is cosine. So where does cosine x equal 0? That would be when x is pi halves and 3 pi halves. Two solutions because they're both in the interval. Okay with that?
Wait. Why do we need to find cosine of x?
That was the derivative. Slope of the tangent, remember, is the derivative. That's f prime of x. Take that derivative.
That's cosine x is. Sorry, my stroke is messed up. Oh, yeah, never mind.
Original. Now, a lot of times when you see questions for Rolle's theorem, mean value theorem, right? Apply a mean value theorem or state why you can't. Apply Rolle's theorem or state why you cannot. Three things must happen. It must be continuous, differentiable on the interval, mean value, different y values, Rolle's same y values. Those three things must be there in order to apply the theorem. In other words, then you'll find those pieces. Okay? To give you a basic graph here. Here was your sine function graph. Well, there's pi halves, there's 3 pi halves, there's 0. You okay there? All right. So, a few things for today. Understand what's required for Rolle's and mean value. Actually computing them, not too bad. Just remember the requirements, okay? You want to remember this guy right here. Okay, if you kind of forget Rolle's, you would at least calculate this and get a 0. So if I can just remember the slope of the tangent, slope of the secant, you know how to compute slope between 2 points. You've already got kind of ingrained in your mind that slope of the tangent is the derivative. You know that piece, okay? Other thing would be probably not a good idea to hit signs with fruit or mailboxes with bats.
No.
It's going to get you in a lot of trouble.
I'll do it. My gosh.
Personal experience to get you in a lot of trouble. All right. So homework here.
Oh, really? Yeah.